All right, good morning, everyone. This is a very brief introduction to oceanography or oceanography in under 5 minutes. So basically, we have five oceans. If you already know, we have the Arctic Ocean, the Atlantic Ocean, the Pacific Ocean, the Indian Ocean, and the Southern Ocean. And they're all defined by the different boundaries, and you have north and south of the Atlantic and Pacific Ocean. And those consist of gyres and stuff. Okay, so how are oceans created? So basically, oceans are created by hot mantle material moving up from the bottom of the mantle near the outer core and rising up through the mantle to the lithosphere. If you don't understand what those terms mean, go watch a video on plate tectonics. We actually have one at the Helix initiative, and you can understand those things a lot more. But basically, just hot mantle material creating ridges in the lithosphere and causing magma to come out and then creating seafloor. And that is what creates oceans. And then the oceans expand towards trenches where then they go down into the mantle and dissolve there. Okay, and so the way basically what happens is that this new seafloor is created, and this process is called seafloor spreading. And we can track the progress of how much seafloor is being generated by paleomagnetism as one of the examples, which basically is caused by little rocks in oceanic crust called magnetite, and they generally point towards the North Pole. And then once we go through a magnetic reversal, which basically means that the magnetic field of the Earth flips, which is a natural phenomenon, basically it will point in the other direction. So basically every few million years, the magnetic field flips and we get different serrated lines like this that's created by the magnetite. And that's how we track how old ocean crust is. And that's how we know that the youngest crust is at these centers called spreading centers or divergent plate boundaries. And that's how we know they get older as we go further out. And that's also how we know that oceanic crust is a lot younger than continental crust, which with the oldest oceanic crust being around 180 million years old. And as you can see, this is a diagram of an actual spreading center near Iceland. And that's why Iceland's so cool, is because it has a lot of geologic activity. You might know that Iceland takes a lot of advantages with their geothermal energy. And that's because they're sitting right on a divergent plate boundary, which generates new crust. Now, this full ocean cycles and creation and destruction of oceans can be viewed through a lens called the Wilson cycle, where basically we have mantle plumes, which are basically just a bunch of mantle material pushing on lithospheric crust in a stage called uplift. And then in the juvenile stage, we get some spreading outward, and it fills into a sea. And an example of this is the Red Sea. And then we get into mature oceans, which is further spreading. And those are the Atlantic and Arctic oceans. And then, as you can see, eventually the destruction of the ocean crust is greater than how much is being generated, which causes a decline in the ocean, which is the Pacific Ocean right now. And then eventually the two land masses that surround the ocean collide together, and that creates the death of the ocean. So this is the start of the ocean, and basically this is all the stages it goes through, and then eventually dies. And then next, we can talk about where does all the salt in the ocean come from. And there's two major factors where the salt in the ocean comes from. And basically, that's basically through weathering or through outgassing, which basically is just stuff coming from the mantle, and just like a bunch of minerals coming through the mantle and just spreading out those minerals and causing the ocean to gain its salinity. In addition, all the dissolved components of seawater are listed here, and all the parts of the ocean have the same percentages of each of the major components of seawater, which is basically all the ions that fill seawater. So as you can see, chlorine is the highest with 55%, and sodium is 30%, and then we have sulfate, magnesium, calcium, potassium, and other dissolved components. And as you can see, the salinity of seawater is around 3.5% salts and 96.5% water. Now, the salinity may vary from ocean to ocean, and that depends on evaporation, runoff, and a bunch of other factors. But the parts of which make up that salinity, how many parts chlorine and how many parts sodium, all remain the same. And this is called Four Cameras principle. which was created by George Forkhammer and was verified by William Dittmar. And it basically says that all these constituents are in the same proportions, no matter how many changes in salinity there are, total salinity there are, or what part of the world that you're in. And that's why we can calculate the percentage of salinity of seawater by using this constant and multiplying that by the chlorinity in percentage. So if you know what the chlorinity is, which is there's a number of ways that you could do that, you find that, then you can find out the salinity of seawater. All right, so let's take a look at how we monitor our oceans. So basically, there's a lot, obviously, satellites. An example here is Jason-2, and that basically uses satellite altimetry to see the heat of the oceans, you know, how it rises and falls, and a bunch of surface topography and stuff like that. And usually satellites use satellite altimetry to monitor our oceans. And other ways that you can get ocean data is by using a human-operated vehicle, or HOV. And that's basically a manned submersible that goes into the water and collects data. And then you can also have ROVs, which is remotely operated vehicles, and they go into seawater and collect data. Or you can have AUVs, which are autonomous underwater vehicles, which is something, it's not depicted here, but it's basically they release it into the water and it goes out and collects data and comes back to the ship without any direct contact with the shipmate, with the ship members. But in ROV, the ship members can control it and investigate what by themselves using the ROV as an extension of themselves. But the AUV just goes by itself and it's programmed to go by itself and find data, and then bring it back. Okay, and another tool that ships use are side scan sonar, which basically means that they can see a bunch of topography, and it's like sonar. So basically they just send out beams, and depending on how long it takes it to come back, they know the depth of the ocean in that area. And by sending out a bunch of beams and multi-beam sonar, they can figure out the topography of the ocean floor. And that's basically how they find all these features, which include the continent and the continental shelves and submarine canyons and guyos and the mid-ocean ridges and abyssal plains and abyssal hills, and also trenches and stuff like that. You can all find those things through various different types of investigation that we listed before. And these are all different things that come with plate tectonics and plate tectonic activity in the ocean. Now, the ocean can be classified into different layers, including the epipelagic zone, which is basically where sunlight reaches, which is 200 meters, and mesopelagic zone, or the twilight zone, which is 200 meters to 1,000 meters, where it's not aphotic, but it definitely has less light. And then bathypelagic is below the photic zone, and then abyssopelagic and the Hadal zone, which is basically all the trenches. And you can basically classify the ocean into these different layers. Okay, let's talk about waves next. So first we have a capillary wave, which is generated by wind, and these are very, very small waves. You can barely see them. And basically the restoring force of what causes it to go back to normal before the disturbance is just cohesion of water molecules. Now, for all other types of waves, the restoring force is gravity. So if we have wind waves, this is labeled ocean waves, but it should be labeled wind waves. The disturbing force is wind, and the restoring force is gravity. Similarly, tsunamis are also restored by gravity, and so are tides and so are stages. But tsunamis are caused by an event such as an earthquake, a landslide, or a volcano, or maybe some calving of some ice sheets. Tides are caused by gravity and the rotation of the earth. And that basically, those gravitational forces from the sun and the moon causes the earth to bulge and create tides. And then the stages are basically caused by a storm front or a storm surge. It's usually caused by some sort of hurricane or storm activity, and that's also restored by gravity. Now let's look at waves in general. And as you see here, there's different ways that you can measure waves through wavelength, wave height, and then you can also measure wave frequency and wave period, just like any other type of wave. But to find out properties of the different waves, you can use different equations. And the way that we apply those equations are by separating waves into 3 different groups, which are deep water waves, which basically means that the depth of the seafloor is greater than half the wavelength. And then transitional water waves, which is basically the depth of the water is between half the wavelength and 1/20th of the wavelength. And shallow water waves are when the depth of the ocean seafloor is less than 1/20th of the wavelength. And then basically, we can calculate wave celerity and wavelength if we know which type of wave it is, and we know all these different properties, then we can calculate it. Now, obviously, it's easier to calculate shallow water waves and deep water waves and intermediate depth waves, but these are just all the different equations that you can use to find those properties. Okay, and I also wanted to mention gyres, which basically are ocean currents that form like circles in the ocean. So as I was saying earlier, the oceans can be divided of the Pacific and Atlantic can be divided into north and south, and that's because we get different gyres. And so we have the North Atlantic gyre right here, and the South Atlantic gyre right here, and the North Pacific gyre up here, and the South Pacific gyre right here. And we also have the Indian gyre, the Indian Ocean gyre, and then we also have the Antarctic circumpolar current, which is not a gyre, but looks very similar to one. And what gyres are basically created by are just currents and wind in general, and then also the Coriolis effect, which is caused by the rotation of the Earth, and also just topography. So as you can see here, it follows the outline of the continents, and it spins in the direction of the Coriolis effect. So in the north, that would be clockwise, and the south would be counterclockwise. And that's how you get these large currents. And you know, if you've heard of the garbage patches in the middle of the oceans, it's usually in the center of a gyre, because once it gets into the center of a gyre, it's very hard for it to get back out. And that's why a bunch of trash collects at the center of the gyres. Okay, and the last thing I want to talk about is thermohaline circulation, which basically is how density of ocean currents is usually the driving force that creates a lot of ocean currents. So the density of water creates those ocean currents, and density is mostly formed through the heat and the salinity of the water. So those two factors go into density, and then more dense water will sink, obviously, and so that will create a driving current. And then as it warms up and becomes less salty, it will obviously move again, and that creates thermohaline circulation. And that's pretty much it. Thank you so much for watching, and I'll see you guys next time.